Swayam Prabha. Digital India. Educated India.
Let us change gears now and go to a slightly different problem, which I would call the problem of momentum transfer. Let us for that look at a ball hitting a wall and bouncing back with the same speed. So it comes in with speed v and goes out with speed v. What has happened to its momentum? Its momentum initially was in this direction. Let me call it P initial, which is m v, and the final momentum is P final, which is minus m v, because it has just bounced back. So the change in momentum is going to be minus 2 m v. I know that delta p delta t, which is going to be minus 2 m v over delta t, where delta t is the time for which the ball was in contact with the wall, is the force that the wall has applied onto the ball. So this is, I'll call the average force. I'm calling it the average because I don't really know how it changed with time. If the wall has applied that much force to the ball also has applied equal and opposite force on the wall. So a ball hitting a wall applies a force on it. Let me now ask, is this average force that I have written as 2 m v over delta t with a minus sign here, same as the force at different instants? The answer I do not know, but let us try to find out. Let us model the ball hitting this wall as if it gets squeezed in a simple manner like this, and the force it applies after being squeezed by an amount x, this being x, is F equals kx, and since this is a hard wall, k is much greater than 0. It's a very large number. So it's like a very hard spring. If it hits and the force is this, obviously after hitting the ball is going to perform a simple harmonic motion, so that I can write this as k a sine omega t, where omega would be the characteristic frequency of oscillation with this k and the mass of the ball. So we see that the force on the ball is of the form roughly as k a sine of omega t. I have chosen sine because initially the displacement is 0. And therefore, if I were to plot it with respect to time, it would look something like, at 0 it starts, goes up and comes down like a sine wave, and at this point the ball has left the wall. Since k is much greater than 0, this peak is going to be very high, Ka, and the time is half the period, which is going to be pi over omega, which is going to be pi square root of m over k, a very small number. So therefore, what you see is that there has been a very large force spread over a very small time, pi square root of m over k, because k is very large, this time is very small. So I may not even observe how the force is varying. All I see is ball hitting the wall and coming back. So in these situations, it's much better to talk about the net change in momentum, which is really f dt integrated from time t1 to t2, and I call this an impulse. Again, a quantity which is related to the net change in the momentum of the particle. Although I have made the force varying like this, a very neat curve sine omega t, the actual may also differ slightly, but the average force was somewhere here. So this is F average, this is F maybe real, and this is F as I have modeled it. But it gives you an idea as to, in different situations, how do we tackle with momentum changes and forces. So in situations where a very large force acts for a very short time, we are going to use the impulse and use the net change in momentum. You can see that our model is quite okay. Take an example of a hammer hitting on the wall. Hammer is made of iron and therefore it's very hard, and the force it imparts therefore is very large. So what we learned from this is that a ball or a particle hitting a wall for a very short time imparts a momentum change delta p to it, which is related to the force applied by it on the wall. Let me now ask, what happens if there were many balls hitting it? One ball comes, hits it, goes back. Second ball comes, hits it, goes back. Third ball comes, hits it, goes back. In that case, if I were to plot the force on the wall with time, is going to be the first ball hits, goes back. Second ball comes, hits, goes back, and so on. I make this process more rapid now, so that these curves start overlapping. In that case, what I would observe is that one ball hits, gives this curve. The next ball hits the wall even before the first ball has not come back. Third ball hits again, fourth ball hits again, fifth ball hits again, and so on, randomly. So the net force may be somewhat like this. Let me make it slightly thicker, which is the sum of all these forces. So if there are many particles hitting randomly, continuously on a wall, we see that there is a net force that is applied on the wall, and this is roughly a constant. How do I calculate this? This is another application of momentum and force relationship. So what is happening is that these balls are hitting at different times, but randomly and overlapping forces. So the net force is something like this, almost a constant with time, and I wish to calculate this force. In a box or on the wall where the balls are hitting and going back are like this. We again go back to how much momentum are these balls transferring to the wall per unit time. So I'll calculate the momentum transfer delta p in time delta t, and this force that I have written here on the left hand side top is going to be delta p over delta t. Let us calculate that as an application of what we have learned so far. So let us take a box where these small particles or small balls of density n are there, and they are hitting the wall with speed vi. So net momentum change for each particle is going to be delta pi is going to be minus 2 mvi. Since I am not worried about the sign right now, only the magnitude, I will just remove this. How many particles are hitting? Number of particles hitting in time delta t is going to be n times V I delta t times the area. This is the area, this is the length V I delta t, and in volume A times V I delta t I have n times this many particles. This many particles are hitting in time delta t and they are each imparting momentum V I. So, net momentum transferred is going to be this, and therefore, I get delta p over delta t, which is n m V I square times 2 times the area. This is the net momentum transfer, and therefore, this is the force applied by these particles on the wall. If I were to calculate the pressure, this would be equal to 1 over area times the force, which is going to be 2 times the density m V I square. You are familiar with such a calculation from your previous study of kinetic theory of gases, but here we look at it from a slightly more advanced point of view. In addition, this example also tells us how, if the flow of these particles is continuous like a water stream hitting a wall or some object, how much force would it apply.